Hello and welcome to Decision Space Geosciences 10ep.5.4 and the What's New video for 2D mapping and dynamic frameworks to fill. In this video, we will cover the solution highlights for the 10ep5 series. We can start with the new features for dynamic frameworks to fill. In EP5, we introduced the complex geology algorithm and an accompanying new method of conformance. In 5.3, the Mistie correction functionality action tab has been added to the DFF workspace along with the redesigned Create New Framework user interface. In 5.4, Mistie correction has been augmented to include surface pick dip azimuth values and log-derived structural edits from horizontal well correlation layers to include additional constraint to framework surfaces and reduce uncertainty. The Framework Surface Conformance tab has been updated to allow for easier application of parameters and give increased visualization of defined conformance values and relationships. New to 5.4 is the option to create high-resolution, pick-prioritized framework to analysis subsurface uncertainty known as a Reservoir Scale Framework or RSF. New functionality added to Grid and Contour was the ability to generate a Hybridmesh output and the addition of the algorithm parameter radial residual fit for surface picks, both as part of the 10ep5.1 release. New to the 10ep5.2 release was a standalone Mistie gridding application, which has two algorithmic methods to correct Mistie and enables horizon input and output. Here are the feature timestamps to help navigate this What's New video. Let's start with DFF and an all-new algorithm for computing surfaces called Complex Geology. This new algorithm is designed to accurately build 3D frameworks in areas of complex stratigraphic and structural geology. This includes the inputs of multi-Z horizons and generating an outputs of multi-Z surfaces. Additionally, a new conformance method is introduced. So now surfaces are built simultaneously and parameters are directly applied to the stratigraphic intervals between two or more surfaces, and this allows the improved application of geologic rules to your models. Let us look at how conformance and how surfaces really shape each other when using the new complex geology algorithm. Instead of using parent-child relationships between two surfaces, conformance is applied directly to the interval defined by two surfaces. So based on the framework's parameters, both surfaces can move to satisfy the conformance settings. There are a lot of options available to control if and how this is done. Complex geology conformance also has a lot more control over the nature of this relationship. You can set minimum and maximum thicknesses, control for the relative strength of the conformance and specify whether the stratigraphy should have a constant thickness or constant thickness trend. To aid in the setting of conformance relationships, you can create groups of surfaces that may represent stratigraphic packages. Surfaces above and below a nonconformity may behave differently, so you can create different groups and apply conformance to each group independently. Let's look at a demo of the new algorithm working. This session has a framework which is modeling compressional geology, characterized by reverse faulting. Complex geology algorithm deals with multi-Z surfaces by splitting the framework surfaces into individual fault blocks based upon the framework's fault network. Splitting the framework into individual fault blocks allows each block to be calculated discretely, whereby only data points within each sealed fault block are used to calculate the framework surface geometry. This means that repeated stratigraphy can be independently resolved as long as the surfaces are divided by framework faults. If we open the section editor, we can see the data, which is used to make up the exampled framework. We can see that we are using multi-Z horizons and a fault network containing low-angle reverse faults. A middle surface is defined by a low amount of irregularly spaced surface picks. To start the creation of our framework, we should first take the top and the bottom seismic horizon and add these to a new complex geology framework. Once the initial build has concluded, we can see that we have framework surfaces that model multi-Z. These surfaces are not yet offset by faults, so do not follow the full extent of the interpreted multi-Z horizon. The next step should be to add the faults to the framework. Once the faults have been added to the framework, we can set up a fault network and also toggle on framework fault offsetting. Once framework fault offsetting has been implemented, we can see now that our framework surfaces are a better fit to the multi-Z seismic horizon interpretations. Now we have the top and base framework surfaces. We can add the additional middle surface to framework, which is only defined by surface picks, as a new framework surface. Once added to the framework, we can see that the middle surface extent does not fully match the seismic-based surfaces, and that we also have cross-cutting relationships between framework surfaces. Complex geology has conformance parameters which allows us to deal with interval layers. To start, we can take the top surface and middle surface and define a minimum thickness, which in this example is equal to 150 meters. We can also take the middle surface and base surface and define a smaller minimum thickness equal to 10 meters. By defining these parameters, what has been achieved is the construction of framework surfaces, which do not cross. We can also see that the middle surface now follows the geometry of the seismic-based surface outside of direct data constraint, as a conformance relationship has been established. We can, however, add further improvements to our framework. One improvement that can be made is through defining primary surfaces. Primary surfaces tell the conformance group which surfaces should be generated first and which surfaces should be generated afterwards. Therefore, in this example, top and base surfaces are generated before the middle surface. We can see here, though, on the left and right extents of the section, that we have unreasonable thickness deviations. A strength of complex geology and an advantage over traditional conformance parameters is how the user can interact with interval thicknesses. The first parameter to take note of is thickness gradient. Thickness gradient is used to inform the algorithm how much two layers defining an interval can deviate. The higher the value, the more parallel the two surfaces will become. This promotes constant vertical thickness. In this case, if we enter the halfway value equal to 0.5 and then refresh the framework, we can see that the interval thicknesses, especially in the areas which have no direct data constraint, become more constant. Like our problem area to the left of the section editor. Another parameter to consider is thickness curvature, which informs the algorithm how quickly the thickness gradient can change and in which direction. We can bring more consistency to our model if we set a value of 0.65 and refresh the model. We can see that the middle framework surface defined by the picks becomes more consistent as it takes on the shape and the rate of change from the surface defined by the horizon, outside of direct data constraint. So the end result here is a framework surface, which is accurately modeled using just minimal data used to define it directly. It is the algorithm and conformance parameters that are able to generate a geologically reasonable result. This shows how the new complex geology algorithm could be incorporated into your workflow to model sparse datasets and multi-Z seismic horizons. Let's introduce the concept of framework data limits. Framework data limits explicitly defines the spatial limits of a model. So now the extent, size, and the shape of the framework is predictable. By default, the framework limits will be the convex polygon around all of the combined surfaces source data. It can also be a user-defined polygon, and additionally you can control if faults are filtered by this polygon, which allows the user to decide whether faults should die out or extend beyond the boundary of the framework. The user can still define each surface's area of interest, which is a smaller view extent of each surface. The framework data limits feature also changes how grid definitions work. The grids now always extends to cover the entire model to ensure that all data is used in the framework surface construction. The user has control over size, shape and rotation of the grid cell spaces. Let us look at another new feature in DFF, which is Mistie correction. Mistie correction has been introduced to DFF as a method of fitting regular sampled seismic horizon and grid data to irregularly spaced sparse surface pick data. The Mistie correction functionality within DFF calculates the difference in depth, also known as the Mistie value between the two datasets. It then applies this correction to the seismic horizon data, ensuring that it matches surface pick positions where they are present. The user can define the radius of surface pick influence. Outside of pick locations, no change to seismic data is applied. This generates structural models that are based on the highest resolution data available without losing the overall structure identified within the seismic data. As a result, Mistie correction allows surfaces to be accurately located at the correct depth, reducing the risk of costly operational mistakes where targets' locations are overshot or undershot. Let's look at an example of Mistie correction in action. In this session, we have a seismic horizon, 3 wells, and an associated set of surface picks that we intend to use as source data for a framework surface. If we turn attention to the section editor, we can see that the horizon is offset from the surface picks and defines the mistie. The mistie can cause problems when generating framework surfaces, due to conflicting data. Constructing our framework surface with this data will mean the surface does not pass through the surface pick data. To correct this issue, we can add the seismic horizon to a new complex geology framework. After the initial build of the framework, we can see the framework surface follows the input seismic horizon very well. The next step is to add the surface picks as a secondary source to the newly constructed framework surface. Despite including the surface picks as source data to the framework surface, we can see that the framework surface still does not pass through the surface picks and instead continues to follow the geometry defined by the seismic horizon data input. To correct this issue, from within the DFF workspace, the user can select the desired framework surface and move to the Mistie correction action tab. The user can enable the Mistie correction, causing the parameter pane to become active, where there is the option of 2 algorithms, simple kriging, or thin plate spline. Mistie parameters can be displayed within the map editor to reflect parameters set. The user can choose to define a radius or ellipse, and also change the ellipse azimuth, if required. Once the input parameters have been chosen and confirmed, the user can click the Apply button and run the selected Mistie correction algorithm. The output from Mistie correction is a difference map and a correction map. The correction map shows the difference applied to the original input horizon, and the difference map shows the amount of correction which was required to pass the horizon through the surface picks to achieve minimal to zero mistie. If we turn attention to the section editor, we can see how the generated correction horizon passes through the surface picks with minimal mistie, while maintaining the structural interpretation from the original seismic horizon. Once the user is happy with the applied correction, we can refresh our framework to incorporate the corrections within the framework surface construction. We can see that after refreshing our framework, the framework surface follows the corrected horizon and therefore passes through our surface picks with minimal offset and correcting the mistie. Furthermore, DFF's Source Data Manager has been fully integrated with the mistie correction functionality to enable data changes to be quickly reflected in the adjustment applied by the mistie correction algorithm. For instance, if the user was to mask this particular surface pick, we can see that to remain synchronized, the Mistie correction performs an automatic algorithm run. If we view the section editor and display our corrected horizon, we can see that the pick that was masked in Source Data Manager is no longer incorporated into the generated correction. This is also reflected in the difference map, and by the absence of a drawn radius for that pick location. Once the framework has been refreshed, in the section editor we can see that the framework surface no longer passes through the pick and instead follows seismic horizon geometry instead. Here we can talk about some updates to Mistie correction in 10ep.5.4. Let's start with the addition of surface pick dip azimuth constraint. As stated previously in the presentation, surface picks are one of the highest resolution data objects available to determine a framework surface's depth position. In 5.4, surface pick dip azimuth values, captured at the point of pick interpretation using tools such as image log sinusoids, can be used as an additional variable in the Mistie correction algorithm. The dip azimuth can be used to impact the surface fit made within the defined correction radius or ellipse. If chosen, it can also have an independent radius or ellipse zone smaller than that of the Mistie correction for more localized fitting. There is also the ability to render the dip and azimuth values within the map editor for better analysis of local structure and setting of algorithm parameters. The inclusion of dip azimuth as an additional framework surface constraint ensures that the local structure trends in the correct position, helping to generate a more accurate structure model, further reducing uncertainty. Let us now take a look at another data constraint added to Mistie correction: log-derived structural edits from the horizontal well correlation layers mode. During operational geology activity, information about layer position within the subsurface is captured within the incoming real-time data such as the log while drilling or LWD. Through the horizontal well correlation application, layers mode, layer boundaries are adjusted and updated when the reference well log or predicted log is correlated to the incoming LWD to ensure reservoir contact. Adjusted layer boundaries result in high-resolution log-derived structural edits, which can be incorporated back into the reservoir structural model, adding additional constraint that reduces surface depth position uncertainty within the local area or zone of influence. The inclusion of data generated from operational geology ensures the creation of an evergreen subsurface model. Here is a demo of horizontal well correlation layer edits being applied to a structural model to update surface geometry. In this demo, the user has already created a horizontal well correlation layers interpretation, and through locked points and layer boundary shifts made some structural edits to match the reference log in blue to the LWD in red. Once the user is happy with the log correlation, a zone of influence can be defined within the interpretation task pane and rendered on the map editor. The zone of influence defines the extent of influence the log-derived structural edits will have on the framework surface geometry, and works in a similar manner to Mistie correction radius and ellipse definition, where maximum correction is applied along the deviated wellbore and returns back to horizon interpretation at the edge of the zone of influence. Once the user has confirmed the zone of influence, the HWC layer interpretation can be saved and the structural edits committed to the related framework surface's source data. After clicking Save and checking the dynamic frameworks to fill workspace, we can see that the Mistie correction algorithm is already running to correct underpinning horizon data to the structural edits made, utilizing the same method used to correct for surface picks. In each framework surface, it can be seen that the structural edits have been added to the related framework's source data as a dynamically updatable in-memory point set, and is prioritized in Source Data Manager second only to surface pick data. Structural edits from HWC can also be seen in the Mistie correction data sources pane as an input constraint, along with the defined zone of influence. Before refreshing the framework, the impact of including HWC edits in the Mistie correction result can be quality checked in the map editor through the output difference horizon. The cube editor clearly shows the amount of correction applied to the seismic data in order to pass the surface through the HWC structural edits. Furthermore, the geometry of the edits can also be displayed and assessed by switching on the in-memory point sets from the source data manager. After quality checking the results from the Mistie correction algorithm, the framework can be refreshed to incorporate the HWC edits within the related framework surfaces geometry. After the framework refresh, we can see that the surfaces are updated to match the structure interpreted in the HWC layers mode. Working with real-time data in operations geology requires iterative updates to obtain the correct structure. Frameworks and HWC layers are fully integrated to allow for dynamic updatability when new interpretations are made. As the user makes new structural edits and commits these to the framework via the Save option, the framework can be updated and refreshed from the HWC interpretation task pane. After refreshing from the interpretation task pane, the user can in conjunction use the map or cube editor to quality check the structural updates being added to the framework. Lastly, the user can repeat these steps for as many deviated wells as required with independently defined zones of influence within one framework in order to create an evergreen subsurface model with reduced subsurface uncertainty within the defined zones of influence. Let's look at some updates, which are focused on how a framework is created. The Create New Framework user interface has been updated to allow focus between global data and parameter settings, and the use of data objects within the construction of your framework. On the left-hand side of the window, global options such as Interpreter, Well Lists, and Framework Velocity Model can be selected and changed without having to close the interface. On the right-hand side, the user can decide how each source data object is used within the framework. This leads to a more streamlined workflow when constructing a framework from scratch, by reducing click count and time taken to make input data amendments. Now let's talk about the updates to the Conformance Action tab in 5.4. The Conformance Action tab has been updated to include a Parameters pane, a Conformance Overview table and a Layers outline. The Parameters pane allows the user to interact with the surfaces which have been selected, whereas the Conformance Overview shows information from the adjacent and non-adjacent layers and the parameters which have been applied. It also includes a graphical group column which shows the boundary type that has been applied to each group. The layer outline shows a hierarchical view of the parameters and set layer relationships, and shows the group, the subgroup and individual layers which make up these groupings. In the Dynamic Frameworks to Fill workspace, we can see that the first change made is the addition of color coding to the group column. This matches the group column in the Conformance Overview table. The coloring is defined either by the youngest stratigraphic surface or the primary surface, which may sit inside that group. We can also see that if I was to select and change the surface type of the 1400 surface to an unconformity, that is also reflected in the group column. Furthermore, we can also show intergroup unconformities, and this helps the user actually see the relationships and the boundary types which are assigned within the framework. We also have the ability to select surfaces from the Conformance Overview table, and we can see that as surfaces are selected, the appropriate surfaces are also selected in the Surface Data table, and also in the Layers Outline table. Users can also set parameters inside this table, and they can also adjust values if required in the Parameters pane. Additional information to each layer can be added to the layer name free text column if required. In the Layer Parameters pane, we can see that there are some new options which have been introduced. We can see that there is now a Maintain Constant Thickness option, which enforces constant thickness across the framework with just the click of a button, with no need for the user to use any sliders or parameter blending. Furthermore, there has been logic added to the pane for when certain parameters are available to the user, so parameters which will have no effect on the framework are not set. For instance, fault thickness preservation is currently grayed out. However, if the user toggles on fault offsetting, then the fault thickness preservation parameter becomes active. Fault thickness preservation has been made an either on or off option, to give the user confidence to determine whether thickness is preserved or not preserved across the fault blocks depending on the geological scenario being modeled, such as sim rift or post-depositional faulting. The user also has the ability to set non-adjacent layer relationships if required. You can see now that by creating the non-adjacent layer relationship, we have actually added a hierarchical group into the framework layers outline table. We can collapse and expand nodes within this table if required to show the layers which are encompassed now by this new subgroup. The conformance overview table also has the ability to show these non-adjacent layers if needed. Now let us take a look at Reservoir Scale Frameworks, a new mode for creating a high-resolution, surface-pick prioritized framework. Reservoir Scale Frameworks, or RSF, is a new mode added to dynamic frameworks to fill to create a high-resolution structural framework which prioritizes well-picked data through Mistie correction and propagation, allowing more velocity parameter control for domain conversion, and includes an uncertainty workflow for capturing, calculating, and displaying subsurface uncertainty, which can be used in reservoir well planning and operations geology workflows. This new mode of dynamic frameworks to fill has a surface pick-centric design from the initial framework setup to managing surface pick constraint from within the DFF workspace. Reservoir Scale Frameworks has the ability for predefining seismic data such as horizons and surface pick relationships from the point of framework inception. Velocity model parameters can be set per framework surface for increased control when converting time data objects to the depth domain. When constructing a reservoir scale framework, Mistie correction calibration of time data objects is a prerequisite step before generating the framework to ensure resulting surfaces are tied to the related surface pick data. In reservoir scale frameworks, Mistie correction parameter values are defined in context of the map editor, to allow for easy parameter iteration and qualitative checking of results before committing to a framework refresh. Another distinguishing feature of reservoir scale frameworks is the ability through a global toggle to define a start point within the framework stratigraphy to propagate correction results downwards through subsequent surfaces, to ensure that surface pick data guides the resulting framework surface geometry within the defined radius and ellipses. By default, reservoir scale framework gridding resolution will match that of the input seismic data to achieve structural models that are based on the highest resolution data available, without losing the overall structure identified within the seismic data. Now let's take a look at a demo of reservoir scale framework construction. In this demo, we will see how to create a framework using the new Reservoir Scale Frameworks mode. We start the framework building process by selecting the appropriate data objects. Here we select seismic horizons and some surface pick interpretations. Within the Create New Framework dialog, under Framework Type, is a new construction mode called Create Reservoir Scale Framework. Checking on this option switches the framework to depth domain and splits the data management pane between a seismic scale surface and a surface pick table. Within the surface pick table, the user can decide whether to assign the surface picks to a surface underpinned by a seismic interpretation or create a surface only using picks as a constraint. This is an important step as defining the surface pick to horizon relationship assigns the data to be used in the Mistie correction calculation later on in the framework construction process. Once the horizon to surface pick relationships have been defined, the user in the Dynamic Frameworks to Fill workspace is brought to the new Seismic Scale tab. Within this tab, users are able to oversee pick data through the new Pick Manager table. Here the user can select quickly which picks are used in framework surface construction. By default, logic has been added to filter out and toggle off picks which have qualifiers indicating that the surface has not been observed in well due to erosion or faulting. As Reservoir Scale Frameworks is designed to create high-resolution framework surfaces, the user is required to manually enter the framework's stratigraphic order, relying on the user's understanding of the subsurface positioning of data, rather than an algorithmic approach. Another addition to the Reservoir Scale Frameworks is a layer-based approach of defining velocity model parameters for the domain conversion of time data. Within the velocity layer definition dialog, the user can define velocity parameters from using either interval velocity or linear velocity values, or by selecting a pre-constructed hybrid velocity model from OpenWorks. Reservoir Scale Frameworks also has the ability to use a hybrid model for all layers, like the method used in traditional framework construction modes. Unless using a velocity model defined at the point of framework construction, velocity parameters are required to be defined on a layer-by-layer basis. Before running Mistie correction to calibrate the input time data, the user can define additional control to instruct how correction is calculated and applied through the new Propagate Mistie global toggle. This global option allows the user to define a start point in the framework stratigraphy to include correction results in subsequent framework surfaces geometry. Toggling on Propagate runs the Mistie algorithm in a sequential manner and ensures all surfaces honor the structure captured within the surface pick data, and helps to minimize differences between framework surfaces and the input velocity model parameters. A simple example of the propagation mode can be seen. Here the correction applied at the pick position on the blue surface is applied to the descending surface's structure before correction is applied to picks related to the pink and green surfaces. Without the propagate mode, the impact of including surface picks would only be seen on the surface they are directly related to. Once the decision whether to propagate has been made, the user can select some or all framework surfaces to interactively define Mistie correction parameters. In Reservoir Scale Frameworks, Mistie correction parameters are defined, iterated, and quality checked in context of the map editor. As in previous version of Mistie correction, the user has the option to define correction within a radius or ellipse with an assigned azimuth to capture data trends. By default, and for ease of identification when working with multiple surfaces, correction definitions are rendered in the assigned surface color, but can be changed to a background contrast mode, if required. Through the Data Sources and Parameters pane, the user can select whether to define parameters for a single surface, or multiple surfaces at a time. The status message box informs the user when all the prerequisite steps have been completed in order to run the Mistie correction algorithm. Clicking OK or Apply will run the algorithm. In Reservoir Scale Frameworks, Mistie correction calculation is broken into two parts. A domain conversion calculation based on the input velocity parameters for each surface, and then a correction fit of the domain converted surface to surface picks location using the defined radius or ellipse. Once the algorithm is run, the user can check the correction values applied by displaying the generated difference horizon, which shows the amount of correction applied to pass the domain converted surface through the related surface picks. The Mistie correction window allows the user to easily amend and iterate Mistie correction parameters if needed. Once the Mistie correction parameters have been defined and quality checked, the Mistie window can be closed and returned to the dynamic frameworks to fill workspace. Before running and generating framework surfaces, the grid properties of the framework can be reviewed. By default, the framework grid vertices and resolution will be set to match that of the input seismic data. This ensures a good framework surface fit to the underpinning seismic horizon interpretation, to generate an accurate structural model. After generating the framework surface, we can review the structure along a representative cross-section. In the cross-section, we can see that the resulting framework surfaces are tied and calibrated to fit to the included surface picks. The domain converted horizons from Mistie correction can be displayed to give the user a before and after view for quality checking. Furthermore, the impact of including Mistie propagation can also be evaluated. In this example highlighted by the black arrow, shows how the fitting of the green surface to the pick's location is propagated down through the framework structure, and impacts the blue and red surfaces. Once the surfaces with underpinning seismic interpretation have been generated and confirmed, the user can start to add pick-based surfaces, which are only observed at well log resolution. These surfaces are added to the Reservoir Scale Framework as a pick scale surface, intended to be fitted between the framework's seismic scale surfaces, and use conformance parameters to guide geometry outside of direct data constraint. Pick-based surfaces are added to the Pick Scale tab. As with seismic scale surfaces, these pick-based surfaces require the stratigraphic order to be entered manually, to ensure correct positioning within the framework. By default, in Reservoir Scale Frameworks, surfaces with seismic data are automatically defined as conformance group primary surfaces. These surfaces are generated first and help to define the pick scale surface resulting geometry in coaction with defined conformance rules. It is also worth noting here that as the base surface is defined as a unconformity, no conformance parameters are automatically defined. For the conformable surfaces in the framework, we will define the maintain constant thickness parameter, which will generate pick-based surfaces with minimal thickness deviation outside of direct data constraint. This is important when working with surfaces located close together. Once the framework has finished updating to include the pick-based surfaces, we can take another look at the cross-section. Here we can see that the pick-based surfaces have been generated between the blue and red seismic surfaces created earlier, in accordance with the defined stratigraphic order. These pick scale surfaces follow geometry derived from the blue surface as defined by the conformance parameters, but deviate to pass through surface pick locations where present. Furthermore, the Mistie propagation is also incorporated in the pick scale surfaces due to the defined conformance relationship. This framework is now ready to be used in the Uncertainty Advisor workflow, which can be toggled on from within the dynamic framework to fill workspace. Now let's look at 2D mapping features, and look at the introduction of hybrid meshes to grid and contour. A hybrid mesh is a surface type object, which is used by DFF, and we have now introduced to grid and contour. The main difference between a traditional grid and a hybrid mesh is the addition of triangles along the grid edge. This means that maps constructed with fault polygons have much more accurate borders and contours along polygon boundaries. We have improved the quality of results returned at fault polygon boundaries and at map edges. To ensure that all data positioned at edges and boundaries is included in surface construction, we have included a radial residual fit parameter to the grid and contour algorithms. So now residual fit and surface generation can be done in one step. This all results in a much faster and efficient workflow. Let's look at a demo of this working. To demonstrate hybrid mesh for grid and contour, we have a horizon, a selection of surface picks and a polygon set, which is intended to be used as fault polygons in the grid and contour model. To start, we can add the data to a new grid and contour model. We can see the option to generate either a grid or a mesh output. The workspace options for grid or mesh are the same. If we generate a mesh output from grid and contour, we can see that the hybrid mesh has smooth intersections with the included full polygons, and this can be best shown through the display options when an etched overlay displays the surface edge, where intersections between the hybrid mesh and polygons is shown by triangles. We can take a look at how this compares with traditional grid outputs. Grid outputs display stair-stepped artifacts, which can sometimes miss data out when intersecting with polygon boundaries. From the generated mesh, a back interpolation table can be opened to see how well the mesh fits to included surface pick data. Assessing the table delta values, it can be seen that the mesh is currently offset from the surface picks. To correct this, we can go back to Grid and Contour Algorithm tab and use the new Residual Fit functionality, which allows the user to define a radius of influence around surface pick locations. Once applied, we can go back to the mesh back interpolation table and review the delta values once again. We can now see that the delta values for each surface pick is now 0 meters, showing our surface mesh is passing through our surface pick locations. Another new feature is the addition of a pass-through algorithm. This algorithm allows the user to input a pre-existing surface grid into a grid and contour mesh workspace. This enables the user to generate a hybrid mesh using the same grid parameters used to generate the grid object type, without having to second-guess original input parameters. The last feature we will look at in this video is the Mistie gridding standalone application. Mistie gridding is a new workflow that allows you to easily correct differences between a seismic horizon and surface pick data, which is achieved by defining a radius or ellipse for the surface pick locations. This workflow can also be accessed from the velocity modeling application, Zone Analysis tool. Let's look at a demo of this functionality. After domain converting time horizons, mistie can occur between the domain converted depth horizon and the associated surface picks, as shown here in the Zone Analysis tool within velocity modeling. We can see that the delta values exist between the horizon and the surface picks. If we inspect the section editor, we can see the offset of the depth horizon to the associated surface picks. To correct the mistie, the user can select the depth horizon and surface picks and open the Mistie gridding tool. Once opened, the user can select the 3D survey associated to the horizon, a bespoke well list, and change surface picks if required. The user has the option from two algorithms, simple kriging and thin plate spline. The option to correct within a radius or ellipse is also an option for selection. The correction parameters can also be viewed within the map editor, such as changes to ellipse definition and the set azimuth. Once parameters are defined, the user can then select what outputs to generate. By default, correction and difference maps are both generated. The user can also choose the rename output maps, if required, after the algorithm is run. By default, two maps are generated, a correction and a difference map. If we view the section editor, we can see the corrected horizon now passes through the surface picks. In the map editor, the difference map shows the amount of correction applied. If we reopen the Zone Analysis tool from Velocity Modeling and select our generated corrected horizon, we can check the delta values again, between the surface picks and the corrected horizon. We can now see that the delta values in the table are equal or close to 0 meters. This indicates that our domain converted horizon now passes through the surface picks. Thank you for watching this video. I encourage you to look at the online help documentation and to visit landmark.tv or contact customer support for more details.